Hey guys, welcome to the first day of 1.4. Today we're going to be looking at continuity. I want to say these notes are a little lengthy, so if you need to take a break, go ahead. They just have a lot of examples that will be helpful as you work through your homework. The content's really not that bad. Okay, so let's talk about what we've been doing. We've been saying for a limit to exist, the limit from the left has to equal the limit from the right. So as you fly in from the left and the right, you want the points to meet up, and we didn't care if this point existed or not, right? That was the idea between limits. When we looked at this before, we had the analogy of the road. So we had the road on the left, road on the right. The bridge was out. If you remember that picture, we really didn't care because we said it didn't affect limits. So I'm going to show you a similar picture where we have the road on the left and we have the road on the right. But now what we're going to have is this bridge. We need the bridge to exist for continuity. So I want you to use these analogies as we go through this and picture this. Is there a bridge there? If there is and the left and the right roads meet up, then we're good. Okay, so continuity. The definition is, if you remember the definition of a limit, do you remember that we needed the left limit to equal the right limit? If this was true, then the limit existed. Okay, so what this is saying is we want the limit from the left to equal the limit from the right. Now the last piece of continuity is saying, see this middle part? That has to be filled in. That's really what this is saying. So if this was a graph, if this was C, we're saying the limit from the left, the limit from the right has to equal the output. Road in, road out equals the bridge. Okay, so that is what we're looking at when we're dealing with continuity. So discuss the limit of the function below. So where is f not continuous? So discussing the continuity of the function below, we would say f is not continuous. Now we're going to cheat a little here and look at this and pretend we're back in Algebra 1. If you remember in Algebra 1, you guys talked about continuity and you said anytime you had to pick your pencil up, like there was a break in the graph. So imagine you're driving along on this road right here, and then you see you have to pick your pencil up to come down here to continue on. So we don't have continuity at -4. You keep driving along, drive. You get to 2. To continue on, you have to pick your pencil up. So we also have the function not continuous at x equals 2. Keep driving along, so pick up at 2. And do you see this hole right here? We have a hole at 4. So we have f is not continuous at -4, 2, and 4. Now, those are some Algebra 1 definitions. What if we had to explain? So how do you know using calculus terms that the function is not continuous when x equals -4? Look up above. You need this left road to equal the right road to equal the output there. So if you look at -4, x equals -4, what is the limit as x approaches -4 from the left? And then remember, we have to state the function we're dealing with. So -4, and you know what, let me write out the other part too. And then we're also going to check the limit as x approaches -4 from the right. Then we can dump some answers in. Here's -4 right here. As you drive in from the left, you end up at 3. Do you see the 3 right there? As you drive in from the right, you end up at -2. Now, there's a hole here. Remember, we didn't care, though. So the existence of the point didn't affect our limit answer. So from the left, we got 3. From the right, we got, looks like a -2. Now, are the left and the right-hand limits the same? No. So if the right and left-hand limits aren't the same, these two guys right here are not equal, then the limit can't exist. Remember up above this highlighting, you need the left and the right for the limit to exist. So if the limit doesn't exist, how could it equal the output? Another way of saying this, let me add this over here, is that you need the limit as x approaches c of f to equal f of c. That's another definition of continuity. All I did in this case was combine these highlighting to say if they both exist, the limit exists. Okay, so this is just right here. I'm showing you why it didn't exist. Why the function isn't continuous there. Oh, let's get this back. Okay, let's go on to the next one. We also claim we don't have continuity at 2. Well, what would be our reason, calculus-wise? We would say the limit as we approach 2 from the left, and let's find the limit as we approach 2 from the right. Okay, 2 from the left, driving in, we end up at -1. 2 from the right, we end up at 5. Obviously, -1 is not equal to 5, so right away the limit does not exist. Therefore, the function is not continuous at that value. Okay, last one. Let's find the limit as x approaches 4 and -4. I'm sorry, 4 from the left and 4 from the right. Okay, flying in. We can probably make this a little larger. Okay, flying in at 4 from the left. Oh, look at this. We're ended up at 2, and from the right it's 2. So what did we just find out? If the left and right-hand limits are both 2, doesn't that mean the limit exists? So the limit, this is good news here, the limit is 2. Those were all bad news because those were different. So we're halfway there. If you, again, look up above at the definition. We have this piece finally. We have the limit existing because the left and right were the same. But is the limit equal to the output at C? Well, look down at your graph. What is the output at C? It doesn't exist. So because f of 4 does not exist, the function is not continuous. Okay, we're going to look at a couple more. So the big idea with continuity is you want the limit to exist and equal the output at that value. Okay, going on. There's 2 parts to the definition of continuity. We want the limit as x approaches. Let's see, what letter did we use? We used C to equal the output at C. This is our plan, right? We want the left limit to equal the right limit and then fill it in. And then we also know that for the limit to exist, the left and right have to be the same. So it's kind of like a checklist. So let's look at the first one. What is the limit as x approaches 0 of sine of 4x over 4x? So in these questions in example 2, I'm going to walk you through the parts of continuity. If you guys remember, this was a special trig limit from, I believe, yesterday, and because 4x is 4x and we're approaching 0, we know that this limit was 1. Now, what is f of 0? Well, if you look right here, you cannot sub a 0 in right here because you have a 0 in the denominator, so you would say that f of 0 does not exist. So if I'm looking at this checklist here, I found the limit, which was 1. I found that this doesn't exist. 1 is not the same as not existing. So right away, we can say, no, the function is not continuous. Okay, so let's just go through these. We want the limit to equal to the output. What is the limit here as x approaches -3? Remember, with limits, the first thing we want to try is direct sub. If you use direct sub here, you're going to get 0 over 1, which is 0. Okay, so that's good. What is f of -3? F of -3, we essentially just did that, is 0. So in this case, going back to the definition, is the limit the same as the output? The limit is 0, the output is 0. This is looking great. Is f continuous at x equals -3? Sure is. What if you had to say why? So why would you explain why? You would say because the limit as x approaches -3, don't forget to say of the function, equals the output at that value. Okay, so we have one that worked, one that didn't work. Going on. Use this function and find the limit. So if we try direct sub, now, before I go on, try direct sub up here. If you sub in a 1, you're going to get 0 over 0, which is indeterminate. Remember, indeterminate meant more work. If a function, if you got 0 over 0 as your answer, there was 3 things that we would try. We had tried factoring, rationalizing the numerator, and combining like terms. In this case, you can see the top looks like it will factor, and it does. Now, remember the issue was when we subbed a 1 into the bottom, we got a 0. But the great news here is you can see that those cancel. So now you're left with the limit as x approaches 1 of x plus 1. Now you are able to do direct sub and get 2. What is f of 1? If you try subbing a 1 in to the original function, you're going to get a 0 on the bottom, which is no good. So f of 1 does not exist. So is f continuous? No, f is not continuous. Why? Because the limit as you approach 1 is not equal to the output at 1. Because the output at 1 didn't exist. Okay, so we don't have continuity here. Now here's a higher level thinking. I would like you to try to pause this and try this one on your own. It's saying, can you redefine f as a piecewise to make it continuous? So can we change this problem to make the function continuous? Do you see here how we were able to factor those out? That's going to create a hole at 1. So let's make note of this. There is a hole at x equals 1. We want to fill in the hole. We did one like this the other day when we graphed, I'll erase this in a second, but x cubed minus 8 over x minus 2. We had a parabola with a hole at 212, if you can imagine or remember that. Okay, so what will this look like? Well, we took this function here and simplified it to be this. So these functions agree at all but one point. So this graph is going to be x plus 1, so that would be a 1 here, and then you have a slope of 1. Okay, so this is the graph of x plus 1, but we're trying to graph this, or this piece. And remember, at 1, the function didn't exist, so what we want to do is you really want a hole at 1. So there should be a hole right here at 1. And just to review with you on how this is working, if I find the limit as x approaches 1, I'm claiming that it's 2. Look what happens. As I fly in from the left, I get this 2 here. As I fly in from the right, I get this 2 here. So that's why the limit exists. At 1, we're claiming the function doesn't exist and there's a hole, and that's what we wrote up above also. So how can we fix this? Do you see we really just want to fill this hole in? So we want this to happen. How do we do this? So they asked us to write a piecewise. So you would say f of x, we have x squared minus 1 over x minus 1. Now this function existed for everything except 1, because that would give us a 0 in the bottom. So what do we want to happen at 1? Try to think about this. At 1, you just want to fill the hole in. That would be 2. So this works because now the limit as x approaches 1, didn't we find out up above that that was 2? Oops, let's use a pen that'll stay. And we want that to be f of 1, which is the definition of continuity. And what is f of 1? They say when x is 1, the output is 2. Okay, so the reason that we care about continuity is because a lot of techniques in calc require that the function's continuous. And then don't forget about just the basic definition from Algebra 1, what that means. Okay, going on. Removable point discontinuity. So if a function is not continuous, it's discontinuous. Okay, so what this problem is saying, or it's in a box, so what this idea is saying, is it's saying if you have this function, and they're saying as x approaches c, we get out. But it goes on to say that f of c is undefined, or f of c is not equal to L. So if this is f, do you see I have right here, I have f of c undefined? So it's saying if the left and the right limit meet up, that's what it means by the limit existing, but the point is undefined, then what we have is a removable point discontinuity, also known as a hole. So we've looked at these already. We could have something like this, or it says the limit doesn't equal the output. Maybe that's there. Either way, the hole is not filled in. What we just did, though, we had a removable discontinuity at this one, where we had our hole right here, right? So what did we do? Didn't we fill the hole in to make it continuous? Okay, so a key thing for a removable discontinuity is f of x can be made continuous by redefining redefining f of x at x equals c. So all this is saying is, hey, if you fill this in, now we're good to go. We have continuity. Non-removable discontinuities means that you cannot make the function continuous by redefining at x equals c. So a couple of these that we've looked at so far have been like our jump function, our infinite, and oscillating. Okay, so what these are looking at is if you have a jump function, so something, you have this, even if I were to fill this hole in, right, the function is not continuous. And remember, for a function to be continuous, the limit equals the output at that value, and look at the limit doesn't exist. If you come in from the left and the right, they don't meet up, so the limit doesn't exist. The other case is the infinite case. What if you had this case right here? Right, do you see in the middle here, this vertical asymptote? So the function is not defined there. So the limit does not equal the output. Lastly, if you recall the other case where the limit doesn't exist, it's this oscillating, where the function actually does not slow down as we're approaching zero. So all of these, we have issues at zero. Okay, a non-removable jump. Here's an awesome picture. If you look on the right, can you see that this left road does not meet up with the right road? Also this case right here. You'll know that you'll have a non-removable jump. So it's just a special case of the non-removable. If the left limit, do you see how that's L1 and the right limit is L2? So if the left and right limit don't meet up, then you have jump, and it's called a non-removable jump. Okay, let's go through 3 now. So here's some examples. Find the x values at which f is not continuous. So to be continuous, remember, I know I keep writing this, let's do it again. If a function's continuous at c, we want the limit to equal the output. So we need the limit to exist in general. We don't want any breaks in the graph. So look at A. Is there a restricted domain? You can't have 0 on the bottom, but there's no restricted domain here. So in this case, f is continuous on the entire number line. So find the x values at which f is non-continuous. There isn't any, because f is always continuous. If a function is not continuous, they're asking us to identify if they are removable or not. Just reviewing what that means, a removable discontinuity is right here, and you're looking basically for a hole. A non-removable. Okay, going on to example 3b. We're looking to see if this function is continuous or not. So we want the limit to equal the output. You can see just by looking at this though, do we have domain restrictions? So look in the denominator. Can this ever be 0? It sure can. So we have, find the x values at which f is not continuous. So at x equals plus or minus 1, f is not continuous. Now the question is, are they removable or not? Let's go back up and look at the removable or not. The removable are going to be such that you can fill the hole in. If you think back about the removable ones, let me go back up just a little bit. Do you see that we had a removable at 1 right here? And if you looked, remember we were able to remove it. It factored away. So a removable discontinuity is going to create a hole, and it's when it can be removed, so that it creates the hole that you could then fill in if you are asked to do so. In this case, this factor on the bottom becomes x plus 1, x minus 1. There's no factors of x plus 1, x minus 1 on the top. So to finish the question, they are non-removable. Okay, we have a couple of more of these to look at. Do you guys see by looking at the bottom that x can't be 3 or negative 3? Because that would create a 0 in the denominator. So f is not continuous when x equals 3 or negative 3. Then we have to classify these. So let's rewrite this as x minus 3, and then x plus 3, x minus 3. Do you see right here that these cancel out? What value created that to be a 0 in the bottom? And that would be an x equals 3. So x equals 3 is a removable discontinuity. And x equals negative 3 is a non-removable. I want to leave that space over there. Non-removable discontinuity. Okay, so again, restating this, we had 2. At 3 or negative 3, we got a 0 on the bottom. The 3, which went here, canceled, and they were able to remove them. So we called 3 a removable. Negative 3 wasn't, and it's a non-removable. Okay, going on. Now, I told you we're going to be dealing with piecewise a lot, so I wanted to add a piecewise onto this. If you look at this one over here, look at the independent pieces. This is a line and this is a line. Those are continuous everywhere. The question is, do these two lines meet up? So let me just throw out some hypotheticals. If one line goes here and the other line goes here, clearly not continuous. The left and right don't meet up. But if the second line picked up here, then we have continuity. So independently, both of these guys, looking at this, both of these in here are continuous. The question is, do they meet up at 2? So we need to check 2. So the definition of continuity means the limit equals the output. We can't just look at, though, the limit as x approaches 2, is that equal to f of 2? Because in this case, we have a break at 2 right here. So we have to expand this part to look at the left and the right. So let's look at the limit as x approaches 2 from the left. 2 from the left means value is less than 2, so we're going to use the top line. So it's going to be 1/2. We're going to use direct sub and get a 2. Now what we're going to do is we're going to test the limit as x approaches 2 from the right. 2 from the right is numbers greater than 2. Remember, we don't care if that's equal to 2 or not. We're looking at greater than 2. So we're going to use direct sub with a 2 here and get 1. Now in this case, 2 is not equal to 1. So because the limit from the left does not equal the limit from the right, the limit as x approaches 2 does not exist. If the limit doesn't exist, then right away the function is not continuous. So to answer their question now, we would say f is not continuous when x equals 2. So at x equals 2, we have a non-removable discontinuity. And then let me ask you this question, is how do we know it's non-removable? Well, nothing factored out, right? They didn't, if you look up here, this was removable, they factored out. We don't have any of that going on, and that's how we know. Okay, so that is continuity. I'm looking at the rest, and it looks like we're dealing with just some extra examples. So that got us through continuity. In your homework, there's some tricky questions with limits. So that's what I'm going to go over the rest with you. But remember, the key idea for continuity is the limit equaling the output. Now, if you look at the next directions, I'm just asking you about limits. Okay, so here's some slightly trickier limit problems. It asks you to find the limit. If you notice, this says 2 from the right. Do you see this plus sign right here? Right, so we're dealing with 2 from the right. Now, when you have a function and you're analyzing the limit and you're just looking at the right or the left, do you remember for the limit to exist as x approaches 2, what this means is the left has to equal the right. So let me see if this makes sense. If the limit as x approaches 2 exists, then that means the left limit has to equal the right limit. So if the limit exists at 2, then those two will also exist. If you try subbing a 2 in, though, do you see that you're going to get 0 over 0, which is indeterminate? Okay, so what we're going to do is we're going to try letting x go to 2 instead of 2 from the right, right? We're really just going to think about it as 2, and if that works, we'll be okay. So let's look at the limit as x approaches 2. 0 over 0 didn't work, so we have to try one of those 3 things that we've been talking about. It looks like factoring is going to work, or at least it's factorable. On the top now, we want an x minus 2, so we're going to factor a negative out. Look at here, those cancel. So now you have the limit as x approaches 2 of negative 1 over x plus 2. And I'm sorry, this was 2 from the right. You can sub a 2 in, and you get negative 1/4. Okay, so even though the question asked 2 from the right, we can just try 2 if we're able to figure it out. Now look on the next one. This problem is asking you for the limit as x approaches 2. When you sub it in, you get 0 over 0, which is indeterminate. Go through your cases, and none of them work. Factoring, rationalizing, or common denominators, that doesn't work. So what we're going to have to do when you have a problem like this is you're going to want to test the limit from the left and the right. So let's test 2 from the left, and we're going to test 2 from the right. So remember, for the limit to exist overall, the left and right have to be the same. If we are looking at 2 from the left, think of a number line just to the left of 2. Aren't you at 1.99999? Right? So if you think about it this way, if you plug any or substitute any number less than 2 in, okay, so let's think what happens. So you sub a number less than 2 in, let's pick 1. So you're going to get 1 minus 2, which is negative 1, and the absolute value gives you a positive 1. And if you sub a 1 in on the bottom, you're going to get negative 1, which is negative 1. Right? We looked at a problem like this earlier where x minus 2 in the absolute value and x minus 2 are the same magnitude. But if this is going to create a negative, this will create a positive, giving you an overall negative 1. So this thing that I wrote to the right is just a thought process. If you want me to go over another one with you, let's try the number 0. If you sub a 0 into the numerator, you're going to get the absolute value of negative 2. A 0 into the bottom gives you negative 2. So this is going to be 2 over negative 2, which is negative 1. Right? So you're always going to get that. I just gave you numbers on the right to make sense of it. Look underneath now. If you sub a number greater than 2 in, so if you have a number greater than 2 in, the absolute values here are irrelevant because you really don't need them because this is always going to be positive and this is going to equal 1. So is negative 1 the same as 1? No way. So if the left and the right limit don't meet up, then how could the limit exist? So what would we say? We would say the limit as x approaches 2 of this function does not exist. If they ask for a reason, it would be because the limit as x approaches 2 from the right is not equal to the limit as x approaches 2 from the left. Okay, so if you have a problem like this, you're going to have to test left and right. If you go back to the beginning, direct sub didn't work, our other methods didn't work, so now we've proven that the limit doesn't exist. Here's a little recap. Don't forget, when the right and left limits are not the same, the limit does not exist. Okay, I told you there was a lot of examples here. Again, this will just help you on your homework. Hopefully there's not too many left. Okay, on this one, we are looking at a greatest integer function. So this function, so a little recall is that this is the greatest integer, n, such that n is less than or equal to x. Some examples are if you take the greatest integer of 4.5, that's really 4. If you take the greatest integer of negative 3.6, that is really negative 4. All that this is saying is if you're on a number line, and what examples did I give you? 4.5? So if you're at 4.5, you just move to the number on the left, the first integer on the left of the number line. If you're at negative 2.4, I'm sorry, if you're at negative 1.3, you move to the left and get negative 2. Okay, so that's really what that means. The graph looks like, you guys dealt with this before when you were dealing with step functions. It looks like this. You can see that the y values between integers don't exist because look at, you're always going to get integers as your answer. Okay, so a limit problem at this one, if they give you a step function, do you see that in the problem? They didn't ask for left or right. You have to know to check it because the left and the right quite often don't match up, kind of like this one. So when you're dealing with absolute value, they didn't ask for left and right, but we knew to check it because we are going to jump here from -1 to 1. Okay, so here's another case. So if you are finding the limit as x approaches 1 from the left of the greatest integer function, here's 1. If you're approaching 1 from the left, so here's the left, do you see you're going to get 0? Again, we don't care if the function exists or not, but if you take 1 from the right, look how different this is. Here's 1 from the right, you're coming in, so here's 1, and you're coming in from the right, you're going to get a 1, which is right there. So what's the answer here? The limit, let me write this in another color so we can see it, does not exist. I'm just writing it up here. And there's our answer. Why didn't the limit exist? Because 0 and 1 aren't the same. The left and the right don't meet up. So remember to test left and right when you're dealing with greatest integer. Okay, going on to this one. How would we know do we have to test left and right? How would we know? So again, look at the problem itself. You have this quadratic, which is continuous everywhere. This quadratic also. The question is, do they meet up at 3? So we need to test the left and the right. So the limit as x approaches 3 from the right. And we need to test the limit as x approaches 3 from the left. 3 from the right, I'm going to use the bottom one because we're looking at numbers greater than 3. And if I sub numbers in, I'm going to get -3 squared plus 4 times 3 minus 2, which is going to give me, is that a 1? And then 3 from the left, numbers less than 3, so I'm using this top piece, and I'm going to go ahead and sub 3 in, and I'm going to get 3 squared minus 4 times 3 plus 6, which is -3. That looks like 3. What are you guys noticing? Do you see that the right does not equal the left? So what's the overall answer to the limit? We could say the limit as x approaches 3 of f of x does not exist. What's the reason? And it's because the left and the right limits don't meet up. Okay, so again, some tricky limits on A through D, knowing when to test left and right even if they don't ask for it. Okay, kiddo, stay strong. If you need a break, again, these are just more examples to help you through your homework. Go ahead and take it and come back to this. We covered all the content early on. Okay, so they are asking us to find the values of a and b such that the function is continuous at -1. Remember, continuity means the limit has to equal the output. Okay, if we look at these independently, we have a quadratic, which is good, a number, which is good, and a line, which is good. So independently, all these pieces are continuous. The question is, do they meet up at these breaks? So we need to figure out, we need the left-hand limit to equal the right-hand limit to equal the output. Because if the left and right limits are the same, then the limit exists. So -1 from the left, we want numbers less than -1. We're going to use direct sub and replace x with -1. Next, we are going to take the right-hand limit. So as we approach -1 from the right, we're going to take numbers greater than -1. So we are going to, again, replace x with -1. And we are going to get -2a plus b. Finally, we are going to find f of -1. And if you look at the middle line, f of -1, they tell us that that is just 4 right there. So if these two exist, right here, this shows that the limit exists. So if the left and right are the same, the limit exists, and then we want it to equal the output. So we need all 3 of these above statements to be the same. We want all 3 of the above statements to be equal. Okay, so now you can solve this however you want. You have 3 equations. Let's look at a minus b. Let's take a minus b equal to 4. So that's taking the first part and the last part. I'm just trying to set them equal to numbers. And then let's also take the second one which is negative 2a plus b, and let that be equal to 4. Oh, you know what? It looks like I have a typo here. It looks like this is supposed to be a minus b, and I put a 4 there. So let me fix that. A minus b equals 4, negative 2. Okay, so this is easy to solve for a, isn't it? Just b plus 4, and then we can sub this into this a. So then I'm going to get negative 2b plus 4 plus b equals 4, which is negative 2b minus 8 plus b equals 4. I can combine the b's and get negative b. I can add this 8 over here and get 12. So if negative b is 12, b is negative 12. Remember the question. They asked us to find a and b to force this function to be continuous at negative 1. So I have my b. Remember over here in the beginning, a is b plus 4. So what I'm going to do is say a is b plus 4. So a is negative 8. So we found our a and b. So what this is saying is if you go back to this problem and if you replace a and b with the values we just found, that all these pieces here, right here, will meet up. Okay, so we'll meet up right there. Okay, again, just more examples to help you out. We finished the notes earlier on. Looking at 6, find f of 2. Okay, well, look at the domain restriction. Do you ever see a value where x can be 2? I don't, so f of 2 does not exist. If I'm finding a limit as x approaches 2 from the left, I want numbers less than 2. And you can see, you can take this first part. Here's where x is less than 2, and I'm going to replace x with 2. And get 4. 2 from the right, I'm looking at numbers greater than 2, so I'm in this piece. I'm going to replace x with 2 again, and I'm going to get 2 times 2 minus 1, which is 3. Now, I don't know if you're noticing this, but look, if you see that the left limit is 4 and the right limit is 3, what can you say? If the left and right limits are not the same, doesn't the overall limit not exist? How do you know you have continuity? Wouldn't to be, for a function to be continuous, you want the limit to equal the output, but look at the limit here. The limit didn't exist, and the output didn't exist, right? So we have no values there, so determine the following. There is no continuity there. Is there continuity? No. F is not continuous at x equals 2. Okay, again, I know this is a lot. Take a break if you need to. Another example, though. A couple of these functions are just functions that I want you to be familiar with. You should be able to graph this natural log function. It is going to look like this, and you have the point 1, 0. If you recall, you need x to be all positive, so your domain restriction is x greater than 0. So when they start asking for h of 0, there's a vertical asymptote here, so this does not exist. If you want to approach 0 from the left would be over here, and look at, there's nothing here. So the left-hand limit does not exist. 0 from the right means to fly in from the right, and look at it, here's 0, right? We keep going down to negative infinity. What's the overall limit? Well, if the right and left-hand limits here aren't the same, then the overall limit can't exist. Okay, this function is actually going to look like this. 3 is a domain restriction. Do you see that in the bottom? You get this function and right here. So if you look at the denominator, x can't be 3. We have a vertical asymptote at 3. So what's f of 3? Well, didn't we just say it doesn't exist? If you take the limit as you approach 3 from the left, it goes to negative infinity. 3 from the right goes to positive infinity. Are the left and right hand limits the same? No way. So the overall limit does not exist. Another thing to point out is if you didn't have access to the graph, how would you do this, right? So this is a little tricky here. You cannot, if they ask for 3 from the left, remember, if the left and right hand limits are the same, the overall limit exists. But you cannot sub a 3 in because you get a 0 in the bottom, right? You get 1 over 0. What you can do, though, and really don't want to write this down. This is just a thought. What number is right to the left of 3 on the number line? Isn't it 2.99999? So if I have 1 over 2.999, and I'm just, in my head, I'm thinking a whole bunch of nines, aren't you going to get 1 over a very small negative number? And do you remember from pre-calc, 1 over a small number is actually a huge number, but a negative huge number is negative infinity. On the next one, 3 from the right, you're right here. So if I subbed in and this is just a thought process, this is not the actual number. If I sub in 3.001, I'm going to get 1 over a small number. And what's 1 over a small number? And we call that infinity. Okay, so that's a way to think through that without the graph. Okay, for this next one, I have this on here because I want you to think through how to find values on the unit circle. When you're thinking about limits, secant is 1 over cosine, so this is how we're actually going to look at this. And if I try subbing in, let's look at our unit circle. Pi over 2 is up here at the very top, right here. So if I try subbing that in, cosine of that is 0, and 1 over 0 does not exist. So the algebra 1, thinking of this by subbing a number in to get f of this, does not exist. Now if I think of pi over 2 from the left, on a number line, isn't that just shy of pi over 2? But remember, if we're using radians, this is 0, and this part up here, let's make this a little more clear, this part up here was pi over 2. So just to the left of pi over 2 is actually right here. So what is the cosine of that value? Isn't cosine of that going to be the x-coordinate, which is right here, which is a super small number? So cosine, just to the left of pi over 2, is a super small number. And cosine's in the denominator. So what's 1 over a super small number? A super big number that we call infinity. Pi over 2 from the right is just bigger than pi over 2. What's cosine of that value? Cosine is a super small, the x value, because that's cosine, is a super small negative. And what's 1 over a negative super small number? And that would be negative infinity. The left and right limits are not the same, so the overall limit does not exist. This idea right here of this small, I'm trying the circle thing again, didn't work, but this idea of writing this out, I really don't want or need to see that. It's just a way for you to think through it. Okay, so those were some crazy limit problems. To wrap this up, here's some awesome pictures. What this is saying is when you're looking for a limit, what this is saying is who cares about this? We don't care what's going on at the value. So you can almost cover it up. It's totally irrelevant. You just care about coming in from the left and the right. Let me do that again once the green is gone. Coming in from the left and the right, and do they match up? Okay, because continuity dealt with the limits equaling the output. If I'm dealing with limits, I don't care about what the output is. I just want to come in from the left and the right to meet up. But when you're actually looking for a function value, you don't care about both things on the left or the right. You just care about the value. Okay, if you put those two together, you end up with this picture on the bottom. So remember, for the limit to exist, for the function to be continuous at a value, you want the limit as you approach C. So this is saying the left picture from above. You want, if this is C as I come in from the left and the right, I would want that to equal the output. Okay, this is what continuity would mean. Is this function continuous? Well, look at here. This is going to be the value of the limit, but this is the value of the function. So this would not be continuous. How could we make it continuous? If we could somehow shift this dot up, right? Then it would work. But as it stands, it is not. Okay, kids, see you later. Bye.